I'm Shawn. I'll tell you a little bit about myself. So I'm not originally from New Zealand. Did anyone notice that? Yeah, I'm from a place called New Mexico where it's dry and brown. Does anyone know where that is? Yay, New Mexico. Well, I did my bachelor's and my master's. My background is in applied maths. And then I had a stint at one of the American National Labs, Sandia National Labs, one of the big DOE labs. And then I came to New Zealand to study. There's a big shot in my field, mathematical biology at the University of Auckland. Did my PhD, and I've done a few postdocs, whatnot, at Massey and University of Auckland, and right now I'm at bioengineering, and I'm studying the womb, critical to the propagation of the human race. Well, also I've done a bit of lecturing, so I get to teach math once in a while, and I notice that my students are quite sharp. They often, like Shawn, you asked such a silly question, like find X. You guys see X? It's right there. Why did I ask such a silly question? Oh, yeah, okay, Shawn, you asked a silly question. And sometimes you can just take little expressions and cancel them, and what do you know? 6 equals 6. That's a relief. I'm glad that 6 equals 6. And if you just follow patterns, right? If you lim blah, blah, blah 8, it's 8 sideways. Well, lim blah, blah, blah 5 is what sideways? 5. Can you guys see this stuff okay? It's hard to see the faces. Okay, thanks. But so sometimes I have artists in my classes, and sometimes they express their despair quite creatively. Poor students. So math is handy. We use it. Medical people use it, like nurses, to calculate drug administrations so you don't die when they give it to you, right? Builders, right? Builders love 90-degree angles. Have you noticed that? And it also makes sure that the buildings that we're in, they don't collapse. Thank you, builders. Thanks for that. And also, of course, when we spend too much money on ice cream, we find how much debt that we're in. Does anyone else have that problem? Spending too much on ice cream? Other things? Oh, okay. So does anyone use a device like this? Like a tablet or a smartphone? Does anyone use these things? Laptops? Have you heard of them? Yes. Okay, just checking. So when these things tell you like how good the Wi-Fi signal is or how many bars are on your cell phone, can you do that without your device? How would you know? Can you do this? Oh, it's pretty good over here. Oh, ooh, Wi-Fi's pretty strong. Oh, no, I think it's stronger over here. Ooh, I can feel it tingling. Is that how it works? Can you do that? Without these devices, would you have any idea how strong the signal is for Wi-Fi or something? Not a clue. So how do we find them in the first place? Oh, someone knows the theme of this talk, right? These things, nobody can see, nor hear, nor taste, nor feel, nor smell. We have no senses that can pick up these things called radio waves, right? Wi-Fi, cell phones, baby monitors. And what was the answer? Someone said, how did we find them? Mathematics. That's a good guess. Thank you. This fellow, James Clerk Maxwell. Has anyone heard of James Clerk Maxwell? Yeah. He was the 19th century Einstein. He came up with these equations, Maxwell's equations. They formulated the relationships between electricity and magnetism, connecting visible light with the invisible and previously completely unknown radio waves that no one had ever seen nor heard, nor tasted, nor felt, nor smelled. Are you glad that Maxwell found radio waves? So we can use these devices? So I can get Wi-Fi? So I can play video games? Anyone else play video games? Okay, I see a few nods. It's hard for me to see. Oh, hi. How's it going, eh? Isn't this a bit strange? Isn't this a bit amazing? It's quite amazing. It's possible to predict what will happen by mathematics, which is simply following the rules, which have nothing to do with the original thing. Richard Feynman. He was one of the big shots of theoretical physics in the 20th century. A very big shot. And quite a character, too. Amazing. What does it say? What does it say about reality? And maybe I can illustrate with just an example. Has anyone ever used a piece of software that there's no documentation? Like you download an app or something? Yeah. So what do? How does this thing work? Right? You start pushing buttons and putting dials. This is an example of a piece of software I used while I was at Sandia Lab, so I could visualize results, my simulations and so forth. See, what's happening? Is it working? And I had to exhaust the knowledge of people around me because I had no manual, there's no documentation. How do I get it to do this and cut through the thing so I can see? Oh, you stand on your desk and you rub your belly and you hope, right? Okay. Well, eventually I exhausted the knowledge of people around me and I discovered, oh, there's a button on this thing. It says help. And I clicked on help and I was excited. I'm going to get help. And you know what happened? It opened up a little window that said, are you kidding? Like, you want documentation? No, there's no documentation. So I used something else, right? But what's the presumption under me trying to figure out a piece of software, or any of us? You download an app and you start fooling with it. How does it work? Right? You assume that it's going to do the task that it told you it's going to do, right? That it wasn't made by a crazy person that just wants to torture you. Although sometimes do you wonder when you get these apps, this is clearly designed to torture me. Next, try a different one, right? Go through until you find one that makes sense. Well, extend that a bit. Driving your car and you turn the wheel and it makes this weird noise. So you take it into the mechanic. Mechanic says, what's the problem? Well, you describe it. It makes this weird noise. And so what does the mechanic do? He starts to diagnose. Well, what's the problem? How do I figure it out? How do I fix it? What's the presumption? That the car wasn't made by a crazy person, right? That it isn't a car that's just made just to torture you, although sometimes I wonder, some cars that I've seen, right? What about, okay, you go to a doctor. Go into the doctor and say, hey, my shoulder makes this weird noise when I rotate it. So what does the doctor do? Start taking pictures and start taking samples and doing tests, trying to figure out what's wrong, trying to diagnose the issue so they can treat it. What's the underlying presumption? That you weren't made by a crazy person, right? That there's a logic, there's an order, there's a way to figure out how it works. This is a bit miraculous. You find it strange that I find the comprehensibility of the world as a miracle or as an eternal mystery. Well, a priori, first principles, basic assumptions. One should expect a chaotic world. A world that's not predictable, a world that makes no sense. But we don't see that. We don't see a chaotic world that cannot be grasped by the mind in any way. The success of a project like science presupposes a high degree of ordering of the objective world. That is a miracle, which is being constantly reinforced as our knowledge expands. That's from the 20th century Einstein, Albert. Like, think about it for a second. If I had a glass and I threw it at the floor, what's going to happen? You're going to say, why'd you do that? Because I knew what was going to happen, right? Because it's going to break. It's going to smash all these little bits of glass everywhere. It's a mess. Oh, goody, I have to clean it up. But in a chaotic world, you wouldn't know what's going to happen. Maybe you throw the glass down and it floats up to the ceiling and starts doing a little dance. And then it gets up on your front and starts writing poetry for us. A chaotic world? Is that the world we live in? What? Do we want to test it real quick? Is there a glass in the house? No, that's okay. That's okay. Has anyone seen this relationship? A squared plus B squared equals C squared. Can you guys see that okay? Okay, I see a hand. Yeah. So I hear some words, I hear some things. Okay, so it sounds familiar. So it's related to like these right triangles, right? Isn't that right? It's something to do with triangles. And what's this thing called? The theorem of what? So usually everyone gets it wrong when I do this. No, it's not Pythagoras. This is the theorem of triangles and things. Right? So you see, there's Pythagoras, right? But apparently Babylonian school kids were playing around with this relationship thousands of years, well, 1,000-some years before the Greeks. This relationship has been discovered or invented numerous times. The Babylonians, the Chinese, the Indians, and then the Greeks, Pythagoras. The so-called Pythagoreans, who were the first to take up mathematics, fancied that the principles of mathematics were the principles of everything, all things. Order, cause and effect. Logical structure, predictable, consistent, universality. That relationship has been discovered in completely different places in space, time, and culture. Was that an accident? And were these discovered or invented? Like, what do I mean by discovered? Like, we're Babylonian school children with their little cuneiform tablets running around and going, oh, look, it's that Greek theorem over there. What, is that what they would say? It's that triangular thing. Shawn's theorem of triangles and things. Right? Or is it inventions? Did these kids just invent something that happened to be the same thing that others invented? So what the heck is math? Sorry, I get excited. Let's look at a dictionary. A dictionary says mathematics is the abstract science of number, quantity, and space, either as abstract concepts, pure mathematics, or as applied to other disciplines such as physics and engineering applied math. Now, always make this addendum, and relationships between number, quantity, and space. Shawn's dictionary addendum. Right, so the relationship, that's a relationship. Right, a lot of mathematical formulas, the equal sign says as long as you're changing these bits on the left, this bit on the right changes. They're related to each other, right? Relationships. Maths is something of a problem. Did you get that? I made it funny. Well, on the one hand, some people think that mathematical entities, they just exist, like in their own little mathematical realm, and that indeed they are discovered, like those Babylonian kids running around. Oh, look, it's the Greek thing. On the other hand, others think it's just fictions. They're anti-realists. They're just completely made up. We invent mathematical entities. They don't exist otherwise. But if you think about them like existing, that suggests some pretty weird things. Like, what if Homer in Mathland, he found the theorem of triangles and things, and he crumpled it up and stuck it in his pocket? What would happen to it on the Babylonian kids with their little cuneiform tablets? Whoa, it just disappeared. And would we lose that relationship throughout all time and space? But then by the same token, why are the same inventions made across space and time and culture? Doesn't look accidental. And on top of all this, well, we can do it. Right? We all do maths in some capacity. Did anyone drive to be here? A couple of us drove. I drove. So when you're driving, do you realize that you're doing vector algebra? Do you see vectors going up? Oh man, that's a big vector. I don't want to go out there. I'm going to die. And so, oh, that's a small vector. Oh, I can make it. Is that how you see driving? Anyone? No, right? Because what we have an intuitive, sense, right? What we do is we just look to see, we estimate, okay, this one's moving so fast. No, I don't want to, don't want to risk it. Oh, so this one's not moving too fast, so I can get in front of it, right? You're doing sophisticated calculations, and you don't really think about it too much. Driving and playing ball. If I was to throw this thing out there, someone could catch it because they're expecting what? A ballistic trajectory, a very familiar trajectory. Oh, catch it. We perform sophisticated calculations. I don't really think about it. Although I have had math students go to extraordinary lengths to avoid an exam. It's amazing how much work students will put in to not do work. Yeah. It's crazy, isn't it? And thinking of how sophisticated they are, did you hear recently about the AI robot that folds laundry? And like how much work went into this? And the guys are saying, this is a hard problem. This is complicated, getting like the folding in its stuff and getting the creases right and everything. And so I'm like, oh, well, so yeah, it's a complicated thing. And we don't really think about it. We just think about, oh, it's a tedious task. I just have to do this thing. But just imagine, ladies and gentlemen, you soon could have an AI robot folding your laundry. If only you have a small nuclear power plant in your backyard to power the thing. Right? AI is just so voracious with electricity. But isn't it amazing that we have this capability to perform such complex calculations? Mathematics incorporates cognitive mechanisms which have evolved like other biological mechanisms by confrontation with reality and which have become genetically fixed in the course of evolution. The logical schemes and hypothetical representations are the same as the logical schemes and the coordination of actions, schemes that have been tested through eons of evolution and which by now are genetically fixed. In other words, doing math is no different than calculating when to pull onto the motorway. Let's put it a little bit differently. There's a lot of words in there. Hypothetical representations, that's just the abstract, like your diagrams on a board or something. Coordination of actions, the athletic or driving, right? This fellow, this evolutionist is saying they are the same. Do you guys buy that? So this basically says that all mathematicians should be amazing athletes, and all athletes should be amazing mathematicians. Is that the case? Yeah, I can think of more than a few counterexamples. I've known a few mathematicians over the years, far smarter than me, and some of them, they struggle tying their shoes. Are my shoes tied? Okay, good. I have one fellow, Bob, is a brilliant fellow, really nice fellow, socially awkward, could hardly negotiate, walking from point A to point B. And he'd come into the lab, like when I'm leaving, like 8 o'clock at night. He was very much a night owl. What you working on, Bob? Oh, polyhedral combinatorics. Okay, Bob, bye. I have no idea what that is. Have fun. And one time he comes in, and he's like, hey guys, can you help me? Do you know anything about the wheels on a car? Because I think something's wrong. I said, okay, go have a look. Bob, you've been driving on flat tires. You've destroyed your wheels. What's wrong with you? He's like, I don't know. I thought something was wrong. I bet. He's like, what do I do? Well, you don't know what to do. So we have to get a tow car. We had to help the guy and get him all sorted, get him new wheels, new tires. He said, don't drive on flat tires. So you can do your polyhedral combinatorics. This conflates two very different ways of thinking. There are different ways of thinking, right? And it's extraordinary how some thinking seems so far removed from survival. One of the oddities of human intelligence is that its level advancement seems like a case of overkill. These higher intellectual functions are a world away from survival in the jungle. Most biologists believe that the human brain has changed little over tens of thousands of years, which suggests that higher mental functions have lain largely, dormant until recently. These functions, if they were not explicitly manifested at the time they were selected, why were they selected? How can natural selection operate on a hidden ability? Think like the evolutionary theory says that natural selection, it sieves like different fins, different feathers, different wings, different legs, different hooves, different teeth, different fangs, or whatever, through the environment. How fit are you? If it doesn't have any way for the environment to interact with the thing, then natural selection can't happen. So if you had all these brilliant abstract abilities that were just sitting around in your head, not interacting with the environment, then evolution doesn't do anything with it. How to get there? Mathematics ought to be viewed as an ever-expanding mansion floating in space with new links constantly growing between previously separated compartments. In other words, a castle in the air. Some mathematics can seem pretty detached, but some of it seems very useful. I like pies. Sometimes I have 1, 2, 3 pies for lunch. And sometimes I forget to bring pies, so then I'm in debt to my mate for a pie, or maybe 1, 2, or 3, so I have negative pies. And sometimes we go in halves on a pie, and we share a pie. I have a third of a pie, he has a quarter of a pie. And because we're math geeks, we like pie. 3.14159. But so these numbers, right? We use them. They're handy. They're useful, especially when you like pie. But did you know that some of these numbers, like negative numbers, there were mathematicians that rejected the idea of negative numbers until as recently as the 19th century. And for some, like numbers, they don't make sense until they're in context, right? So negative numbers, how do they make sense? Right? I can't really have a negative pi. I can't have like a negative length. I can have a negative attitude, right? Or I can be in debt. Right? You have negative money, credit cards, yeah. Sorry. Or you could be underwater, right? So you could have depth. And what's another one? Oh, so how cold is it? Right? You're freezing, you're below zero. So negative numbers, they do make sense within their context. Sometimes it's difficult to grasp what's going on with them. Okay, so you ready for some maths? Okay, Shawn. Okay. It won't be too bad, I promise. Does anyone recognize this complicated shape? A square. Are we all in agreement? It's a square. Okay, it's a square. This square has side length x What's the area of this square? X squared? X squared? Okay, that's what the slide says. We must have got it right. Yay, x squared. Okay, so what if I throw a curveball at you and I say, guess what? The area of this thing is -1. What does that mean? That means Shawn made a mistake. Right? Usually that what means. If I'm filling a board with a bunch of calculus and stuff, and I get, oh, I have a negative area. I made a mistake. My students are like, hey, Shawn, 2 times 3 is 6, not 5. Oh, okay, sweet. But what if it is? What if that's what you get stuck with? You're trying to solve this. X squared equals -1. Like, what does that mean? Like a negative area. Does it have meaning? Well, think about this. Remember this stuff from primary school, like the multiplications of signs? How do you multiply signs to get a negative? Can it be the same sign? So it's usually positive, positive gives you a positive, positive gives you a positive, thank you. And a negative times a negative gives you a positive. The only way to get a negative is to have a mix, to have a positive and a negative. Thank you, thank you. Class participation, thanks guys. Right? Is there any way to take numbers multiplied by themselves using this little pattern and get there? Right? You're taking a square root of a negative. What the heck does that mean? Right? What is x? It's a visitor from another world, another dimension. Any Alice in Wonderland fans? Right? It's an Alice in Wonderland number. Oh, you can't really read that. Let's go this side. The issue was bumped into the centuries until about the 18th century. Since the idea of a number producing a negative area, like I thought, oh, it's just a mistake, or x squared equals -1 was considered impossible. When mathematicians would run into this doing calculations, they just chucked it. Oh, this doesn't make sense. Oh, this is ridiculous. Right? So no one really dug into this thing. No real number solves this. But remember the progression. In natural numbers, and expanded to integers because we added negative numbers, and then you keep growing. Real numbers satisfy this. X equals square root of -1 doesn't. Maybe we need more numbers. What do you think? Numbers from where? What kind of numbers? Alice in Wonderland numbers. So imagine the rules for multiplication for signs. Something a little different. So I'm going to throw a curveball at you tonight. Here we've got a pair of axes, got -1, +1. Think of these as having degrees. So we start on this side and rotate around. So this is 0 degrees, this is 180, and this would be 360 coming around in a full circle. So far, so good. If I multiply 1 times 1, what do I get? Oh, just 1. Just go with 1. And so if I'm doing rotations, that's the same as doing a complete rotation around that circle, and I get back where I started, right? 0 plus 360 puts me back at 1. With me so far? Okay. So what if I go 180 degrees? If I start here and I rotate halfway, where am I? So halfway around, what number is there? I'm sorry? -1. Yeah. That's the same as multiplying +1 times -1, and I'm sitting at -1. It's just a different way of viewing something that you've been doing probably your entire life. Now, if I multiply -1 times -1, I'm going to get back where? -1 times -1 is what? +1. How many degrees do I add to get there? 180. So if I start at 180 and I want to get back to where I started from, I need to add that 180 degrees. So far, so good. Most people don't see this is where some of these sign multiplication things come from. They just give you the table and then you plow through it in primary school, right? Okay, so I'm going to throw another curveball at you. What if instead of just bouncing between +1 and -1, I go here? And I shift up by 90 degrees. Okay, well, what number is that? Wait a minute, it's not -1, yeah? It's not +1. Is it 0? Any takers on 0? Anyone say 0? No one's going to say anything because they don't want to take a test right now. I didn't come here to take a test. But so it's not at 0, right? It's up here. So it's not 0, it's not +1, it's not -1. I tell you, let's just give it a name. I. I'm going to go with I. You can name it whatever you want. I. So for multiplication land, this is the same as saying 1 times I gets me to I, right? Now what if I take starting here and I move another 90 degrees? Where does that get me? I'm going to be at 180. What number is that? -1. So if I just rotate 90 degrees, I'm at -1. Now the way I presented this is kind of like multiplying these numbers. So that's the same as I times I. In other words, I squared equals -1. Hey, look at that. We just got a number times itself that gives you a negative. Did I just break maths? Well, actually, no, there's a really smart guy from the 18th century that came up with this. I'm just showing it to you. Right? You can continue this process. You can keep going around the circle, adding these angles and multiplying by numbers. But what we've done is we've traveled along the real number line, the real numbers that make sense, that give you length, that give you volume, that give you, weight. Right? Real numbers. But along these, we've invented these other numbers. We call this the imaginary, because we're imagining these I's running along this axis. And it turns out when you put these together, you get these things called complex numbers, which are on the board right here. Z equals A plus BI. That's a complex number. It combines reals and imaginaries. And it turns out, just like the number systems that have grown over the centuries, the real numbers are just a small part of a larger world of numbers called the complex. The complex numbers that are like Alice in Wonderland numbers. Like, what is I? I don't know. So I told you all that until I squared equals -1 is defined, and it was ridiculed by Descartes. Anyone familiar with Descartes, the philosopher mathematician? He mocked these. He was like, these cannot be real, these are imaginary. And that's why they're called imaginary, because they mocked them, right? But that simple little quadratic problem cannot be solved with any number called real. And mathematicians were very disturbed by that for centuries. So I showed you all that so I can tell you, who cares? You guys feel much more complete in your heart, don't you? Finally, we can solve x squared equals -1. Thank you, Shawn. That's been torturing me. Yeah. Well, the people who care, the mathematicians, right? There's no longer unsolvable algebra problems. Right? So now the numbers are considered complete. Nobody's bumping into these weird problems. You end up using complex, and it's done. And imaginary numbers are considered beautiful mathematics. Okay, does anyone agree with that statement? Do I hear any calls for beautiful? I hear it, nah. Nah. Okay, so who are the jokers that thinks it's beautiful? Well, mathematicians, right? And actually, one of the primary motivations for mathematicians to do maths is their appreciation of the beauty of mathematics. A mathematician, like a painter or poet, is a maker of patterns. The mathematician's patterns, like the painters or the poets, must be beautiful. Beauty is the first test. There's no permanent place in the world for ugly mathematics. In fact, this goes a bit further than just, it looks nice. A while back, an issue of the Mathematical Intelligencer asked readers to rank mathematical theorems in order not of accuracy, not of power, or usefulness, but what do you think? Their beauty. So I don't know if you can read all this stuff in this bad screenshot, but there's a bunch of statements and mathematical formulae in there, some of which I have no idea what it is, not my field, right? Very esoteric. But so the votes came in. And in the eyes of the mathematical beholders, a queen of equations arose and paraded around on the ramp like a donut on legs. Any takers on what that equation was? Anyone want to guess? Oh, that would be a good shot. Yeah. Almost. But it's got an E in it. E to the I pi plus 1 equals 0. So this little fellow. It ties together the natural number E. Is anyone taking calculus or dealt with compound interest? Natural number E. It also ties together the ratio of circumference diameter pi, that familiar number you can't escape, that also tastes pretty good when you carve it up. And fundamental binaries, 0 and 1. And look what else is in there. Our little imaginary friend I. So it's considered beautiful. So what? Who cares? Well, the mathematicians. Does anyone else care? I care. Oh, but I guess I don't count. I'm a mathematician technically. I have degrees. So one common question that I hear is there any use for this stuff? Are they connected to the real world in some way? Or is it just mathematicians at play, frolicking about? I introduce you to a nifty equation. This is called Schrodinger's equation. Schrodinger's equation is used for quantum mechanics. Solutions to Schrodinger's equation describe not only molecular, atomic, and subatomic systems, but also macroscopic systems, possibly even the entire universe. And that's from the fountain of knowledge, Wikipedia. Wikipedia is useful for math and not much else. Right? But look at this equation. Look who's in there. There's Planck's constant, it's a charge on an electron, and what do you know? Our imaginary friend is sitting there, embedded in an equation that describes everything. If quantum mechanics is correct, imaginary numbers are a necessary part of the mathematics of the universe. That's kind of weird, don't you think? And in fact, experimentalists have tested to see, do we really need to use these complex numbers in our equations? Yeah, they tried to do it with just real numbers. And it fell apart. Oh, I think that is, yeah, it's part of all that mess with physics. Yeah. Yeah. Do you find that strange? That a number that was put together, that was just labeled to handle irritating mathematical problems for mathematicians, like a visitor from Alice in Wonderland, turns out to be related to the fundamental descriptions of the universe. Right? Strange? Yeah. It's very strange that mathematicians are led by their sense of beauty to develop formal structures that physicists only later find useful. Physicists generally find the ability of mathematicians to anticipate mass needed and the theories of physics quite uncanny. It's as if Neil Armstrong, when he set foot on the surface of the moon, had found in the lunar dust the footprints of Jules Verne. How the heck did he get there? What led him there? How did this mathematician pull this off? Well, it's beauty. Richard Feynman, one of the most important things in this theoretical physics business is to know when you are right. It's possible to know way ahead of checking all the consequences. You can recognize truth by its beauty and simplicity. What an extraordinary statement. So it's not just the mathematicians. But here he's saying, I know when I'm onto something, when it looks beautiful and simple. This is coming from one of the titans of theoretical physics of the 20th century. One of the big shots. And he's describing the techniques, the skills that were honed over decades as a successful career. I'm onto something. Like a detective, right? You can smell the trail. Well, follow the money. Right? He's following what? Beauty and simplicity. And he's not alone. I was thus led to a long calculation, the longest in my career. Full of local tactical tricks, the calculation proceeded by twists and turns. There were many obstructions. But always after a few days, a new trick was somehow found that pointed to a new path. The trouble was that I soon felt I was in a maze, and not sure whether, in fact, after so many turns, I was anywhere near the goal when I began. This kind of strategic overview was very depressing. Several times I almost gave up. But each time, something drew me back, a new tactical trick that brightened the scene, even though only locally. Finally, after about 6 months of work off and on, all the pieces suddenly fitted together, producing miraculous cancellations, and I was staring at the amazing, simple final result. These are the words of the co-Nobel laureate, Chen Yang, as he was doing his derivations. I've had a taste of this. I am no Nobel laureate, that's for sure. When I did my master's, when I was doing real maths, some of the derivations you do is just pages and pages and pages and pages. And it's just to get to one big ugly chunk of math. Okay, put that over there. Now I have to do this big ugly chunk. Pages and pages and pages. And then you bash them together. Okay, so this hopefully will go somewhere. And just a giant ugly mess. But now, hey, wait a minute. That bit will cancel that bit. This cancels that. And and out falls something. And you get that sense, I'm onto it, right? This means something. It is clear that Yang's confidence in his calculation is bolstered by the miraculous cancellations he experiences. But such thinking is obviously anthropocentric, very human-centered, and even childlike. What has miraculous simplification of the notation we use in describing nature got to do with nature itself? Well, what do we see in nature? We see complex patterns that are beautiful. And some of them are generated with very simple expressions, very simple mechanisms. Anyone heard of Fibonacci? Right? And these patterns continue throughout nature. We have Schrodinger's equation. We have Newton's laws. We have E equals mc squared from Einstein. We have Maxwell's equations. Thank you that we have Wi-Fi and we can play video games. We have a squared plus b squared equals c squared, the theorem of triangles and things. The most beautiful theorem. And what's this one over here? Everyone's favorite from high school algebra. Minus b plus or minus square root of b squared minus 4. Oh, gosh. Do you remember that? It's like traumatic. The quadratic formula. You remember that thing? Right? A human sense of beauty leads to truths of elegant yet complex relationships. And we see this all over the place. This little equation here, this simple little formula generates what's called Mandelbrot's set. Fractals. Anyone heard of fractals? Right? These things are fantastically complex, and they come out of this very simple little relationship. Fractals have been discovered in nature, like the vein distributions in a leaf, or the branching of our lungs, or the fjords of Norwegian coasts. And as you dig deeper and deeper into the complexity of things, that just seems to keep going on and on and on and on. Eventually, you start staring at the place where you started. It's a little eerie. What does all this say? Philosophy is written in this grand book, The Universe. It's written in the language of mathematics, and its characters are triangles, circles, and geometric figures. There's an order to it. There's a mathematical structure. It doesn't look like it was made by a crazy person, right? It's useful. Hey man, it's beautiful. It's simple, it's complex, with bits from an alien world. And it describes everything. Why? I said all that to bring you to this question. Right? Well, you guys have heard of evolution, right? So evolution has answers for many things. And here's an evolutionary answer. The mathematical structure of the universe allegedly guided evolution to man's mathematical ability. Okay. The athletic cause and effects, along with physical realities, gravity, inertia, friction, are equated with the abstract, logical, deductive powers. Such ability apparently includes aesthetic appreciation for bizarre fictional entities. Somehow natural selection operated on these abilities when they were dormant for thousands of years. Such fictions result in strange entities disconnected from reality, like a castle in the air. But to all these points, why is the universe mathematical to begin with? How did it get that way? It sure is nice. The athletic and the abstract, they are not the same. That's too untrue. Bob the mathematician and his polyhedral combinatorics and destroyed wheels. Why does a human sense of beauty lead to truth? Why would those be connected? This natural selection operating on abilities that were dormant, it contradicts evolutionary theory. It doesn't make sense. Right? And it turns out that these fictions, like imaginary numbers, they're actually deeply embedded in reality. This has triggered many philosophical discussions for centuries. And some of the philosophers, the naturalists, the anti-theists, their answer is, we're just lucky. That's pretty spectacularly lucky, don't you think? It's just a happy coincidence. And that's what one of their texts actually says. So if you're okay with this just being a lucky coincidence, then maybe I could give you $10 and you go to Sky City and give everyone $1,000 when you come back. Right? What are the odds of that? What are the odds that we live in a universe that's so structured, so ordered, so predictable, so mathematical? Theists, on the other hand, what do they say? Well, God did it. God made it that way. God made the universe on a mathematical blueprint, architecture in his mind. What did Feynman say? You can recognize truth by its beauty and simplicity. Has he answered Pilate's question as he's staring truth in the face? I am. Beauty and simplicity. Our sense of beauty, these ideals, our sense of simplicity and truth, these ideals are tied together. Well, not only did God make the universe, what else did he make? He made us. We are made in the image of God with mathematical abilities akin to his divine ability, just a slim reflection of, I can't imagine the math God does. Yikes, right? But also, this is a user-friendly universe. All those relationships that I've shown you, simple, elegant, but also very useful. Like we can have Wi-Fi so Shawn can play video games. That's useful. It even leads to oddities that we reject that later turn out to be fundamental to its description. Mathematics is a language that describes relationships and quantities in the world precisely. It's useful. It predicts and calculates things like we could never hear, nor see, nor touch, nor taste, nor smell. Thank you, Wi-Fi. I can play video games. Does anyone get the idea I like playing video games? You're right. Related to the intrinsic architecture of the universe, seemingly alien discoveries or inventions lead to profound revelations about the nature of reality. And it's a distinctly human endeavor. Universal ideals, beauty, simplicity, lead to truth about reality. And that has a very simple answer. Why? Well, God did it. God made the universe. He made it on a mathematical architecture. And he made us. And he gave us the ability to use math to figure it out. He also gave New Mexicans the best Mexican food in the world. So coming from New Mexico, I struggle with the Mexican food here. But I thought I'd just torture you with, a picture of some good enchiladas. And that's the desert valley where I grew up in Albuquerque, New Mexico. And I guess if we have time for questions. But all the same, thanks for having me out so I could share on one of my favorite topics. And thanks for sitting through the pop quiz. Do we have time for the quiz? All good. Thank you, ladies and gentlemen.